Because in the formula, curl is in here. Do y'all remember how to do curl? Okay. I'll remind you when we go through an example. So let's go back to that problem that we had just a second ago. The one that we got 80 pi on. Help me out here. We had a vector field that was what? Y, z, oh, I remember 2x z e to the xy. Okay. And we had our curve, which was this guy, like that. That was c, but z was 5, and it came from x squared plus y squared was 16. Is that right? Okay, so it was that curve. It was sitting up here a little bit off the xy axis. There it was, right? So we wanted to do that. We did that. We got 80 pi. But Stokes' theorem says that if this C is the boundary of any surface, right? Any surface. So a natural surface for us to look at here would be that disk in there, right? Look at that disk, that flat disk in there. If I call this S, then what I can do is instead of doing the line integral and doing the parameterization and doing the partial and all that crap, right? Instead of doing all that, I just need to figure out if I can do it's basically you're going to do the flux of the curl instead of the flux of that. That's what we're doing. So we just have to find the curl of this first. So what is the curl of F? Well, that's where you have to set up that weird kind of determinant looking thing. Partial with respect to x, partial with respect to y, good. Partial with respect to z. Then you put your components of F here. E to the xy. And then you do that little determinant thing. So let's do that. This will be a vector, right? Curl is a vector. So we cover up the I components and do a determinant there. So what's the partial with respect to y of this? X e to the xy. X e to the xy. I don't remember that as being my answer. Hold on a second. Okay. No, that's okay. With respect to y, that's this. And then partial with respect to z of this. And it'll be minus, right? Minus 2x. I want to see if any of you can foresee where we're going here. Can anyone tell me the only thing that's going to matter from this curl? And why? The z. Why? The z component. Because we're going to use the fact that this surface has a normal that points up only, which means that the normal is 0, 0, 1, which means when I dot it with the curl, the only thing that matters is the last piece, right? But we'll compute the whole thing anyway. All right, good. Partial with respect to x of this is y e to the xy, but negative, right? Because it's the j. And then, where am I? Here. Here to here, I get y, but it's supposed to be minus, but then it's subtracted. So plus. All right. And then last one, and this is the most important one, right? Partial with respect to x of this, 2z. And then partial with respect to y of this. Is just what? Z, but then subtract it. So minus z. Agreed? So now I'm going to try and find the double integral over S of the curl of F dot ds. I'm going to realize that that's the same as, and please understand, curl of f is just a vector field, right? It's like if I didn't do anything, if we forget this whole other picture and just, I started the problem off, and if I called this f and asked you to find flux, that's where we are. But this is the f we're working with, not that f. Understand? It's the curl of it that we're plugging in here. So I know that this is the same as the curl of f dot n ds, right? Not s vector, s surface area. And I'm using this because I know s has a nice normal vector. And why am I using the one that's up? Yeah, we're going to do positive orientation, which means as we move around like this, that's counterclockwise is positive. We look out to our right, our normals should point up. So what is the normal vector we said? Normal vector is the vector 0, 0, 1, which is k hat, if you like. Now dot curl, so dot that with n, and you just get this, which was just z, wasn't it? So we have the double integral over s of, what did you say? Z ds, that's it. But what was z? Z was 5, wasn't it? Z was 5. So double integral over s of 5 ds. And z was 5 because we were up there, right? And take the 5 out, and this is 1 ds, and that's just the surface area of s. And that, be careful on that, that is pi r squared. What's the radius of that? 4, right? So the radius of this circle being 4 is pi r squared. 16 pi is this area. So we have 5 times 16 pi, which is 80 pi. By no coincidence. So I would say, yeah, there's a little bit of trouble there with the curl computation. You do have to be careful with that. But I do prefer that. I do like that compared, to what I would have done with the line integral. And it's amazing that it didn't matter what you would have used for your surface there. You could have used like a top hemisphere. As long as that was the boundary, it would have still worked. All right. What do y'all think? That's the line integral. Yep. Over the vector field. It's work. It's work. Okay. Yeah. If the field, it depends on what your field is and stuff, but you could look at it as work. Yeah.
When we find the magnitude of the flux vector, what is that going to be? Is that going to be just the scalar of the flux? Is that what it is?
Well, the flux is a number.
So when we find the magnitude, that's the actual flux. So that's what it's going to be.
I'm not sure.
Say that we have that vector, right? We came up with it, the one that you did the determinant for.
The curl?
Yeah, the curl.
The curl of f. What about it?
So that's going to be, the magnitude of the curl is going to be the flux, right? So
No.
There's something I'm misunderstanding.
The magnitude of the curl, the curl of the vector field we're given is the new vector field that we're looking at in the surface integral. All right, let's go now and look at this. I have, I think, 2 examples or 3 examples in here. Okay, let's look at this one and appreciate the work we're not going to have to do. All right, so we have a line integral over C, where C is the triangle with vertices 1, 0, 0, 0, 1, 0, 0, 0, 1, and the vector field is given there. So we have, let me draw it first. Let's draw our curve in three-dimensional space. 1, 0, 0 is here. 0, 1, 0 is here, and 0, 0, 1 is up here. So we're getting like one of the faces of a tetrahedron, right? But just that triangle right there. And we need to move around this C, right? And we want to know the line integral along that. And here's our vector field. Now, if you were not going to use Stokes' theorem, what would you have to do? You split it into three separate curves, right? You would call it like C1, C2, C3. You would have to find parameterizations for each of those curves, which are line segments, right? So we could do this. It's not impossible to do. It's just tedious, right? Then you'd have to evaluate your vector field on the curves, each for C1, C2, and C3. Then you'd have to dot those with the derivatives of the curves. And I mean, it could be done, right? It could be done. Let's see if Stokes' theorem is any easier. So if I'm going to use Stokes', I need to see if there's a surface that's the boundary of. Well, I think just that triangle, right? That surface right there, that triangle connecting the 3 points, that plane, right? It's a plane. That's what I'm going to call my surface S. And I can go a little further. It's flat, so maybe I could find its normal, right? And its normal should always be the same, because it's a flat sheet. It's always pointing in the same direction. I could do that. But at the end of it all, we're going to have to find the curl. So let's see if we can get the curl, right? I'm just thinking through this a little bit, okay? Like, okay, this is a surface. Am I going to have any trouble figuring out what that surface is? No, I've done this before, right? I've figured out how to find the equation of planes. It's not terrible. But the curl part might be a little messy, so let me go ahead and do that. Partial with respect to x, partial with respect to y, partial with respect to z. And x plus y squared, y plus z squared, z plus x squared. I'm going to let you do this on your own. I'm not going to do it up here. You should get negative 2z, negative 2x, negative 2y. So there's our curl. It's not so bad when you work through it. All right. Good. Now? I can find the normal vector, right? Let's see. If I find the normal vector, I'm going to have to do some vectors and cross them, right? I find some vectors. We've done this, right? Way back, chapter 10 is where I first did this, right? So again, I'm going to save us some time. If you were to take some vectors in here and cross, you would get a normal vector of 1, 1, 1. Here's the reason I'm not going to proceed with that super shortcut. The reason I'm not going to proceed is because what kind of saved our ass last time was that a lot of these got zeroed out, right? And the one that was left always seemed to contain the variable that was fixed, right? Like when x was 2, it turned out to give us 4 times the area of that circle thing back from earlier. Or if x was 0, just zeroed the whole thing out. Do you see that if I do normal dotted with this, do you see that nothing's going to go away nicely? So what I'm going to do instead is I'm going to use this normal vector to come up with the equation of this plane. And again, we could do that because we know all the points, right? This is the normal vector, so it should look like, 1 x minus x naught, 1 y minus y naught, all that stuff. If you do all that, I'll just use this point right here, 0, 0, 1. You get that. And so you come up with x plus y plus z equals 1 when you put them all together. Now, what value does that give me? If I know the curl, right, that's my new vector field, and my surface S is given by this equation, what can I do?
Solve for one of the variables.
Solve for one of the variables. Which one would you like to solve for?
Z.
Z, right? Make z a function of x and y. And now you're doing what we started class with. You're doing a special case of a flux problem right now. The only thing that's changed is this, where that came from, right? So I'm doing the following. The line integral over C of f dr has become the surface integral over S of curl of f dot ds. But that has become a special case where I'm going to integrate over d. And I'm using a special formula from 13.7 when my surface S can be written as a function of two variables, which is 1 minus x minus y. That's this solve for z. So there's my special function of x and y. And what's my PQR? Here, right? Don't make that mistake. PQ and R comes from your curl. So this is my PQR. And I'm using, let's see, g of x, y, the top one. My normals are pointed up. Yes?
Why is that a y?
Y is where a y?
Where you dotted the normal with the quick equation?
Where I dotted the... Oh, why is this z? Yeah, sorry, this should be z. Thank you. I did it right here. I just didn't do it right there. All right, so we good? Y'all okay with the normals are pointed upward? The z components of any vector on that plane in that octant there are going to be pointed up a little bit. All right, so I'm using the standard formula, which is negative p partial g with respect to x minus q partial g with respect to y plus r dA. So negative p for us would be 2z, but then times the partial of g with respect to x, which would be negative 1. Then minus q would become plus 2x. But then that's a, oh no, partial of g with respect to y, which would be negative 1. And then finally, plus r, minus 2y. dA. Let me clean that up. They're all negative? They're all negative? Do you want me to pull a negative one out or just leave it? Pull it out. Negative double integral over d of 2z. I'm going to leave a space here intentionally. Plus 2x plus 2y dA. This integral can only have what variables in it? X and y, because I switched, right? I'm a special case. That's what z is. So I want to replace this z with 1 minus x minus y. So please remove this 1 minus x minus y, and something real nice is about to happen. I believe the 2x, this is going to give us a negative 2x, and it's going to cancel, and a negative 2y, which is going to cancel, and all you're going to be left in here is a 2, right? So here's where we are now. We have negative, and how about the 2 that's in there? Can I pull that out? Negative 2, double integral over d of 1 dA. And that is the area of D, which is where? It's the base of the tetrahedron, because that D was going to be the restrictions